Hello everybody. Today we're going to be talking about diffusion and effusion. You probably remember diffusion from biology class. When you learned about it, you learned that diffusion is when a substance moves from an area of high concentration to an area of low concentration. This happens gradually, it's spontaneous. Gases are always moving. As you know, they have a lot of kinetic energy. So as they're randomly moving, they tend to move from an area of high concentration to an area of low concentration. For instance, if I were to spray perfume, it would gradually spread throughout the room. Okay, and remember, gases also have the ability to expand. That's a physical property of gases. And the people in the back of the room are going to be able to smell the perfume after a few seconds or a few minutes. And that's because it is gradually spreading from an area of high concentration, which would be the perfume bottle, to an area of low concentration, which would be the room. Now, effusion is very similar. The big difference here is that effusion is when gases pass through a very small opening from one container to another. Okay, and this is usually pressure driven. So what happens is when effusion occurs, you have a tiny opening and the gases are forced from the area that has the higher pressure to an area of lower pressure. Let me give you an example. If I were to blow air into a balloon and without tying a knot, if I were to release the balloon gradually, the air comes rushing out of the balloon and the balloon deflates. That little area, that little tiny opening is allowing the air to come out. And the reason it's coming out is because the pressure inside the balloon is higher than the outside. Another great example would be if you poke a hole on a tire, okay? Or when you're taking air out of a tire. You see, air is going to exit the tire through that tiny opening. This is an example of effusion, and it is pressure driven because the pressure inside the tire is much higher, so it's going to force air to go out. Okay? Now, not all gases have the same velocity. Okay? Notice on the bottom here, it says that the rate of effusion or diffusion is directly proportional to molecular velocity. What that means is that the faster the gas moves, the faster the rate of effusion or diffusion. You see, we have a mathematical formula called Graham's Law of Effusion or diffusion. We can apply it to both. And what the formula says, or the law says, is that the rate of effusion of a gas is inversely proportional to the square root of the mass of its particles. If you look at the formula written below, you're going to see that R1 is going to be the rate of gas number one, whatever that gas is, whether it's oxygen, carbon dioxide, hydrogen, helium, you name it. And then you got the rate of the second gas. We're going to compare how the rates of one gas versus the other, and you're going to see that when you compare them, you're going to learn that the lighter gases tend to move faster. There's an inverse relationship between the molar mass of a gas and its velocity. So if you look at the bottom here, the faster that a gas moves, the higher the rate of effusion. And when you look at this ratio between the rate of gas 1 and the rate of gas 2, according to Graham's law, it is inversely proportional to the square root of the molar masses. Now pay attention to this carefully. Notice that the molar mass of gas 2 goes on the numerator, and the molar mass of gas 1 goes on the denominator. Notice that, look at this relationship right here. The rate of gas 1 and the molar mass of gas 1, notice how they are on opposite sides of the equation. One is a numerator, the other one's a denominator. The same thing with the second gas. Okay? So be mindful when you set this up that you put the molar mass of gas 2 on the top and the molar mass of gas 1 on the bottom. So that's what the M stands for, molar mass, okay? And if you look here, we mentioned how mass and velocity are inversely proportional. The lightest gas known to man is hydrogen. Hydrogen is diatomic. If you go to the periodic table, you will see that hydrogen has a molar mass of 2.02. It's 1.01 times 2. Helium is the second lightest gas known to man. From the periodic table, you'll see that it has a molar mass of 4. And these are in grams per mole. As gases get heavier, for instance, oxygen, the molar mass would be 32. You're going to see that the heavier the gas, the slower it moves. Okay, so that's also very important. Now, there's also a relationship here between velocity and kinetic energy. You see, the faster that something is moving, the more kinetic energy it has. A lot of you are going to be taking physics in the future, and you're going to see this is a formula on how to actually calculate kinetic energy. To find kinetic energy, what you do is you get half the mass, okay, and then you square the velocity. Notice the importance on velocity. Out of all the variables here, velocity is the one that's being squared. And that's because kinetic energy is dependent on velocity. So the faster you're moving, the more kinetic energy you have. Okay, so keep that in mind. All right. So one of the things we're going to do is we're going to use Graham's law of effusion or diffusion to compare how much faster one gas goes versus the other, okay, in terms of the rate of movement. So if you look here, here's an example of what we mean by this, okay? So we want to know how much faster does a sample of methane, if you recall methane is CH4, so how much faster will methane gas effuse compared to carbon dioxide gas? So here's what we're going to do. When you set the problem up, okay, first I would advise to find the molar masses. Now, obviously, they're saying that methane is faster than CO2, okay, and the assumption here is that methane is lighter. Well, we're going to prove it. If you go to the periodic table, carbon is 12.01, hydrogen is 1.01, but there are 4 of them in methane, so that's 4.04. The molar mass of methane is 16.05, okay, grams per mole. Now let's do the same thing with carbon dioxide down here. Again, carbon is 12.01, oxygen is 16, but you got 2 of them, so that's 32. When you add this up, you got 44.01. Clearly, carbon dioxide is heavier. So based on what we discussed earlier, methane will be the gas that diffuses faster. The question is, how much faster? Here is where Graham's law comes into play. What you're going to do is put the rate of the faster gas on the numerator. The faster gas is methane. You're going to divide that by the rate of the slower gas, okay, which in this case is CO2. Now, remember what I told you guys. When you put the molar masses, okay, the molar mass of gas 1, which is methane, goes on the bottom. So the 16.05 goes down here, okay, that's grams per mole. And then the heavier gas goes on the top over here, and that's 44.01 grams per mole, okay? And notice what you're going to do, and there's many ways you could do this on the calculator. What they want is how much faster. So really all we want is the ratio between the rate of the faster gas versus the slower gas. So one of the things that I do first is I simply divide. And if you divide this, you get 2.742. But then you got to get the square root. Okay, don't forget to do that. Okay, that's the last step. So when you divide 44.01 divided by 16.05, you get 2.742. And if we get the square root of that number, you're going to get 1.66. Okay, this is the answer. Methane will diffuse 1.66 times faster. So we can put it over here. It goes 1.66 times faster. Okay, we're talking about methane over here, than CO2. Okay, and that makes sense because methane is the lighter gas. So this is how much faster one gas goes over the other. Okay, we'll do one more example in just a second, okay? So this is the formula that we just used. It's known as Graham's Law of Effusion. And as stated, it's the rate of effusion or diffusion, we can use it for both, of a gas is inversely proportional to the square root of the mass of its particles. Let's do one more. Let's take, for instance, hydrogen, which is the lightest gas known to man, with a molar mass of 2.02 when you multiply 1.01 times 2. Let's see how much faster hydrogen is compared to, let's say, something like oxygen gas, which we know is 16 times 2, which is 32. Now remember, the units are grams per mole. What you're going to notice is when we place it in the formula, you're going to see that the units cancel. So here's what we're going to do. The rate of gas 1, so let's put here the rate of hydrogen, okay, over the rate of oxygen. Put the lighter gas on the numerator, okay, the rate, and then the heavier gas, because we want to find out how much faster hydrogen is compared to oxygen. Then look what happens. Here's where you got to remember the setup. Remember that the molar mass of hydrogen would go on the denominator. Okay, notice this relationship over here. So you're going to put 2.02 grams per mole down here. And then you're going to do the same for oxygen. You're going to put that at the top. And you're going to put this up here like this. Okay, now we'll do the math in just a second. But you'll notice that these guys cancel out. And then when you divide 32 by 2, you're going to get, by 2.02, you're going to get roughly 16. I'm going to put here 15.84. This is roughly 16. But you got to remember that we got to get the square root. Don't forget to do that final step. Okay? And when you get the square root, you're going to get that hydrogen is 3.98, approximately 4 times faster, okay, than oxygen. Okay, so the hydrogen gas is going to be almost 4 times faster than oxygen. All right. Now, one more thing that I wanted to remind you of. We were looking for the rate. Sometimes they might give you the ratio of the rates, and you might be asked, give you one of the molar masses. Let me go ahead and erase this here for a second. You could work backwards where they give you this ratio and they give you, let's say, one of the molar masses and you're asked to find the other. Okay? If you're being asked to find the heavier one, then you're being asked to find the top one. If you're, that's the way you set it up. Okay? If you're being asked to find the lighter gas, then what you do is you set this one. You're looking for this one down here. So you just got to read the problem to see if they want you to find one of the molar masses. Always remember that the way we set it up, the heavier one is the one we put at the top, just like we did over here. Okay? And then one final note I wanted to tell you. Imagine if I had containers, and in one container I had oxygen gas, another container I had helium gas, and in another container I had carbon dioxide gas, and I allowed them to, whether it's diffusion or effusion, I allowed the gases to escape. And let's say over here, this is the back of the room. Eventually, all these gases will make their way and fill the room. Okay, this is what effusion and diffusion is. Gases have the ability to expand. Now, because these gases have different molar masses, they don't get to the back of the room at the same time. Who do you think is going to get there first? Okay, and who do you think is going to get there last? Well, the answer to that is find out their molar masses. Well, earlier we mentioned this guy is 32 grams per mole. Helium is the second lightest gas known to man after hydrogen. And this one is 4 grams per mole. And if you recall, we had found the molar mass of carbon dioxide to be 44.01 grams per mole. So here's what happens. Since helium is the lightest gas, helium is the one that's going to get there first. Okay? The second gas that will get there will be oxygen gas. He'll get there second. And then the heaviest gas in this example is carbon dioxide, and he will get there third. So notice that the velocity is inversely proportional to the molar mass, meaning the lighter the gas, the greater the velocity. That's why helium gets there first. The heavier the gas, the slower the velocity, and that's why CO2 in this example gets there last. Okay? So the only mathematical concept that we added here is that we now have a formula known as Graham's law that allows us to compare the rates of effusion and diffusion of these gases by comparing molar masses. Okay? And I hope that basically mathematically and conceptually, we're able to answer the question of the relationship between velocity, molar mass, and kinetic energy. All right, that's it.